The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody. This is Dr. Mansour, and today is the 6th of June, or June 6th. Today is Saturday, and we have so this is our meeting here, and this is for the AM, the Civil Brits AM. One more session is remaining for this series of free workshops. However, I owe you one period before, to the best of my recollection, so I will find another slot and add another session here. We still have one more session to meet on the 20th, and I will squeeze another session, as I mentioned, in order to accommodate or to make up the period that I missed before. So I will let you know, and it will be the same ID, so there is no need to do anything other than just come and join me, and the computer will notify you with the changes. Transportation tomorrow is the 7th of June. I have a transportation from 9 to 12. Let me see, I think I made a change tomorrow. No, still the same. And and I have seismic tomorrow also, series of seismic webinars or seismic free workshops. If you'd like to attend, I believe it's available on our website also, if I'm not mistaken. Yeah, it's available. Okay, my staff, they put it for the seismic. The surveying and seismic is here. Yeah, so tomorrow is the 7th. That's correct, from 1 to 5. For 1 to 5, and the ID is available on my website. You are very welcome to do that. So if you'd like to join me tomorrow, transportation in the morning from 9 to 12, and from 1 to 5, the seismic, the special California seismic exam. I taught it last semester based on the current code or the new code that started in January. So you are very welcome to attend. Still have tomorrow, and they have additional 2 sessions are coming. The construction, they are coming also, by the way, on the free webinars. So those of you are taking construction in the afternoon, here are the dates. So 6, 13, 27, 28. I believe there is only one change, minor change. There was a conflict, but 6, 13 and 6, 27 and 6, 28, 3 more sessions for the construction depth, if you are taking the construction depth. And tomorrow will be transportation, and I still have 2 additional sessions for transportation. So do your best, and I will do my best. So I try to email you as much as I can, whatever I have. Is your video camera on? The answer is yes. Let me switch to the camera and see if the camera is working or not. Here it is. The camera is working on. And let me see if, let me make sure that here it is. I will turn it on and off, and the audio. So I open it and close it. Hopefully that everybody got the camera, audio, and the video. It's okay right now. That's good news. Okay, thank you. Yes, it was on and off probably. Okay, so I try to do your best, and I will do my best. Just stay healthy, and I will do my best to stay healthy and pray for you. And I hope that everything is okay. Last time I gave you a series of previous exams. I don't know if you got a chance to look at it or not, and I'm expecting that you're going to ask me when I will send you the solution. Yeah, I will do all my best. Let me do my best here with all these books around me. So the exams I sent it to you last time, if I remember correctly, it was fall 2017 and fall 2019, exam 1 and 2. All these things are discussed or sent to you, 3 exams, and also the mini exams that I gave it to those of you who are taking the class with me. So already I would be glad to send to all of them. I think 5 or 6 mini exams. Some problems are very similar or maybe similar to what is in these exams. And also, by the way, I was teaching surveying today for California, and I decided to add additional 2 sessions for the California Special Surveying exam. And the 2 sessions I added, I will make them free. So I will send also the ID for that if you'd like to attend the free surveying 2 sessions, 2 additional sessions to help those who are taking the exam this month. So, so I will send it to you also today. So this is a separate. So you have seismic and surveying, and the let me get some paper here because I ran out of. So the and they try to send you the notes also. So the 7 a.m. And transportation BM and construction BM, all of them, they have only one ID, and the surveying or the seismic, for seismic, it has its own ID, which is available, by the way, on our website. You can, and the surveying, the 2 surveying or the 2 additional surveying sessions, I reserved them this morning, and the ID I will write it to you. I will get the ID, okay, for this and this. So try to do your best if you are interested to attend any of these, if it's going to help you. So the exams, I hope that you get a chance to go over them, and I'm sure that you will have some questions, and I will be glad to answer any, and I hope that I can squeeze any time to get these things. I have all the solutions. Some of them are typed, some of them handwriting. It's just a matter of I'm trying to push you or encourage you, let me put it that way, to do it in your own. At least you can challenge yourself, and when you get the solutions, you can compare it. One topic that that I received a couple emails from some of you about Bosnick's formula. And Bosnick's formula is developed by this French scientist, and the increase in the pressure due to a load can be calculated using this equation or the nomograph that has been developed later on. So as all of us know, if this is OG, the original ground, and if you have a point like point A at a depth Z, so we have two types of pressure. We have the vertical sigma V and sigma H, horizontal and vertical. And the vertical stress that will be developed at this location is basically due to this weight of the soil above this point A, whatever the gamma of this soil. So the weight of this soil is going to create the vertical stress. And the relationship between the vertical and horizontal, we have K sub A and K sub B and so on. This is due to the weight of the soil itself. But Professor Bosnick, he developed an equation to account for any surcharge, any load, in addition to the weight of the soil. We call it surcharge. And this surcharge, it could be either a concentrated load acting over a point, or it could be a distributed load, uniformly distributed load. And this load, W, which is the uniformly distributed load, it could be a rectangular load, it could be a square, or it could be a circular load, it could be a strip load, a strip over long, okay? So a strip, so it could be a circle, okay? It could be a square or rectangle, or it could be a strip load that, so whatever load we have on the surface of the ground, the OG, the presence of such load is going to increase the stress at point A, for example, due to one of these loads. And we need to know that. We need to know that. And you might be asked about this in either in the AM or the PM. So the first equation that Professor Bosnick developed is given as follows. Let me bring the equation and I will be glad to elaborate on it. Move my stuff here. So in any geotechnical book or any review book, you will find this equation. Let me bring the equation. So the equation by Professor Bosnick is given. This is the equation. If you don't have the equation, I will be glad to make a copy of this and send it with my notes. It's called Bosnick's equation. Bosnick's equation. So this is the sigma z, the vertical stress caused by a point load. So the illustration that goes with this equation, if this is a point load P, a single concentrated load acting at point A here, and at any depth Z at a different location, I need to get how much the increase in stress due to this concentrated load. So this is, they call it vertical stress increase, okay, due to a point load. So this is the equation that I'm sure that you saw it before. under a concentrated load 3b over 2 pi z cubed divided by r squared plus z squared raised to 5 over 2, or we can use some kind of factor, c sub r, b over z square, and they developed this table for us in order to get this coefficient c sub r. So you could use the original equation, or you could use the coefficient c sub r based on r over z. What is r over z? R, this is the distance here, radial distance, radial. And r is equal x squared plus y squared square root. So the radial distance is equal the square root of x squared plus y squared. So if I can get r over z, so whatever the r over z, z is the depth. Z is the depth, how deep this point below the load, and where is this point in relation to the load. If the load or this point immediately under this load, so in this case, the R is equal 0. So if the point immediately under the load, so the radial distance obviously is equal 0 because there is no x or y. But if the point is far away from the concentrated load by a distance x and distance y, we can get the radial distance by using Pythagorean theorem, and we can get the. So this is the original equation that listed in geotechnical books. After that, the Department of Navy, they took this equation and they translated into monographs or graphs. So it is a Bosniak stress contour chart. This is one of them. And he is telling you this is under circular load. So one map or one nomograph is developed for circular load. So if the load is in the nature like footings, a circle or a column, okay? So in this case, this circular load, we can find the additional stress. So this is the 2R, which is the R is the radius, 2R is the diameter. So this is the diameter D. So if you do have a load in this nature, and you have the value of this load as a distributed load, the intensity, we call load intensity. And if you know how deep it is, here is using H instead of Z. And how far from the center of the load, call it R. So in this case, we can use this equation that delta for the increase of the pressure is equal I times the application of the load. This is W, or the applied load. So I is called influence value or influence factor. So it's called I. So here it is, influence value, I. So all what I need to do is to calculate. So if I have a circular load, I have a circular load acting on the OG or at any level, not necessarily to be at OG. And this is 2R or simply D. And this is a W, or he call it B application, BAPB, the applied load. Is uniform load. It has certain intensity. It's called load intensity. Intensity of the load, intensity. So based on that, at any point at a depth H or Z, as he called it, at any distance from the center of the load, I can find what is delta sigma V. Okay, is equal the I, the influence value, times the W or the P And these charts are available. I can send you a clean one if you want me to. This is uniformly distributed circular footing, and they developed one on the following page for a long strip footing, for a square footing, and there are many different formats available in most of the geotechnical books. So we need to understand how can we get the additional increase in stress due to a load acting. And I believe, if I'm not mistaken, I don't know if I have a problem here or not, in one of these sample I sent it to you last time. If not, I can grab another set of questions, and I might see one of these problems. It seems to me, let me grab one of the problems in one of the mini exams. Okay, I think it seems to me that if I remember correctly, there was a problem in the geotechnical. Yeah, I could use it in the geotechnical section. I could use it, and I think it will serve the purpose. If I still remember. If not, I will have. And in the many exams, but I don't have all of them here because this during this period I'm using a lot of my stuff spread everywhere. So The is not handy for some reason, so I will skip it until I locate it during the break, and I'm sure that we will go over it. But basically, this is what, or I can use one of my problems in this book here. I have two mini books, okay, in chapter 3, and we can apply it. And after that, the circular one, I can find it. For example, a problem, here it is. Just one of the problems in one of my books. A 1,000 point load acts on the surface of the ground. What is the stress increase 5 feet directly below the load? So basically, this is a straightforward application. So if I have a point load of 1,000 pounds, and this is the OG, so he is asking what is the stress increase below the OG, and it is 5 feet under. So this is a 5 feet, H or Z, whatever, and this is a point A. So we are looking for the delta sigma V, and the stress increases, okay? And he's talking about the vertical stress. So in this case, the equation I showed to you, which is a Bosnick's formula, I can apply it directly, and I say that sigma Z equals to 3B over 2 pi, and this is Z cubed divided by R square plus Z square, and this is raised to power 5 over 2. Or if I'd like to use the factor, C sub R times B over Z square. Either one of them will give me the answer. Since this point A, let me call it point A, immediately under the load, so the radial distance is equal 0. So I can say that this 3B and Z cubed divided by 2 pi, and the R is equal 0, so this is Z square raised to 5 over 2. I can plug the numbers now, which is 3. The load P is 1,000 pound. Oops, so let me make it 1,000 here. And the Z is 5 feet. So this is cubed, divided by 2 pi. And Z square is 9, as 5 square is 25. So 25 raised to power 5 over 2. And you will get an answer based on this equation. Okay. If I decided to use the C sub R factor, so I will go to the table like this, and this is available in all geotechnical books. Since the load on the surface here, and this is a concentrated load, and the point is under the load directly, so the radial distance is equal 0. So the R over Z, R is the radial distance as illustrated in this diagram here. So this will give me C sub R of 0.4775. So in this case, I can use this approach, and I say that, oh, the C sub R is equal 0.4775, and B is 1000 divided by Z square, which is 5 square. So if you do this calculation, let me see if I have calculator here. So it is 0.4775 enter, and 1000, and 25 divided. So it is 19.1 psi, PSF, sorry, per square foot, because the distance 5 is 5 feet. The same story, or the same number, was supposed to get it from here, and the exponent and all these things already, you know how to do that. So it is 25 enter 2.5 and 2 times, and try to do it also both ways just in case. Second by times and where, and 25 1000 times 3 times, I get the same 19.09 or 19.1, so 19.1 PSF. This is an easy and straightforward problem. This is the increase in the vertical stress due to the presence of a concentrated load. And this problem could be modified. Instead of directly below the load, it could be, say, that it is 5 feet away or 10 feet away, or he can give you a diagram like this, that the load is here, this is the 1000 pound acting somewhere here, and this is the point I'm interested in. He will give you the dimension X and the dimension Y, and he will ask you what is the increase in the stress and the vertical stress due to this. So this is easy and straightforward, and I will be glad to make a copy of this when I send it. But let me, since we are here, and another problem about stress distribution and the average stress distribution using the 2-to-1 distribution. If you do have a load like this, 10,000 pounds, and acting uniformly over 4 by 4 square footing, so we know sigma is equal P over A. This is normal stress or axial stress, B over A. So the stress at this level here, it is the 10,000 pounds divided by the area, which is 4 by 4, and this will give you how many PSF? Pounds per square foot, because this is 10,000 pounds and this is 4 feet by 4 feet, so it's uniformly distributed load. And normally we assume that the load is going to generate a uniform stress, except in the vicinity of the load where we have something called the stress concentration. Nobody will ask you about that. But if I have a surface that's 5 feet below, so what will be the average stress distribution that on a plane that's 5 feet below the footing itself? So the depth here is 5 feet. So one concept is 2 vertical, 1 horizontal. Concept. So 2 vertical, 1 horizontal concept could be used. So the surface area here, this 4 by 4, Right now, the dimension B and L, if the dimension here B times L, if it's square, so in this case B equals B, but normally we express it as a rectangular, and if they are given as a square, so B equals L, the dimension at a depth Z using the two vertical, one horizontal, is going to be, the new surface area is going to be B plus Z times L plus Z. Because if this depth is Z and this represents 2V, so horizontal is half of it, half of this. So I have Z over 2 and Z over 2. So half Z on each side. So I will add it to the dimension B. And the same story with the other dimension. So this is the new surface area that will be available at a depth Z. So in this case, we can say that the average stress, sigma vertical, is equal to the load, whatever the load is, 10,000 pounds, divided by the product of the two dimensions of that plane, which is B plus D times L plus Z. So in this case, we have the 10,000 pounds B and L are equal because he said that 4 by 4, and the depth is 5. So 4 plus 5 times 4 plus 5. So this is 10,000 divided by the surface area, which is 81, 9 times 9. So it gave me about 123.46 BSF. And this here, by the way, this problem here, the closest one is answer A, 19.1. And here, this is the closest one is 123, so it is 125. So the stress increase or the stress distribution is very, very important. Okay, so this is something that I need you to be aware of. So the other cases, the one I was talking about, they are important and they are really sometimes tricky. And while I'm talking, I remember the problem, the one I was referring to. I may have it, and I did. I remember where it is. Yeah, this is a typical problem related to the stress increase due to a surface load or due to a surcharge load And let me give you, I know probably you may say it's not fair that I have a problem that I never really solved before. That's good, but at least you can read it right now. And we can work it together and you will get a copy of it after. So if you look to this figure here, this figure shows, and I'm referring to this problem here, a bridge pier is supported by 4 circular footings as shown. Each footing carries 200 kips. The 4 footings are arranged to form a square 50 by 50 using figure 2. Figure 2 is the Bosenics, like similar to what I showed you in my book. Okay, it is the same, came from the same source. It is the design manual. Probably some of you have it. 7.1, the naval facility. They took the equation by Professor Bosenics and they put it in a form of nomographs like this, or figures like this, in order to help us to figure out. So if you look to this, that the 4 footings are arranged to fit square, okay, you determine the increase in the vertical stress. Here it is. So this is increase, not the absolute. Okay. At point P, which is the center of the square, at a depth of 24 feet below the bottom of the footing. So each footing is carrying 200 kips. .200 kips is a concentrated load. This is a circular, so I can get sigma is equal P over A. So the uniform stress that will be acting on each footing is P over A. B is given to be 200 kips. And the area, since the diameter is given to be 12 feet, I can say the area is by D square over 4 or by R square. I will use the diameter by D square over 4. This is going to be KSF, by the way, kips per square foot. The diameter is given. Each footing has a diameter of 12 foot. So in this case, piece of cake by D square over 4. Don't forget that the area of a circle is equal by R square or by D square over 4. Whatever is convenient for you. Don't hesitate to write even a simple formula that we memorize it, but during the exam, maybe a formula like this is not going to be very easy to remember. It is divide by 4, divide by 2, so whatever is convenient for you. So if I took this, the 144, and 4 divided, and second by times, and this, and you multiply this by 200, so I got 1.77, I will round it, kips per square foot. So this is the first thing that I will do. I will convert the concentrated load into a uniformly distributed load over the footing as given. Okay. The second step is, this is a circular uniformly distributed load, but the point that he is interested in is not under the load, is not at the edge of the load, but here. And this is a plan view, by the way. This is a top view or plan view or top view, whatever you like to call it. You are looking from the top. So in this case, I need this dimension is given and this dimension is given. This is 25 feet from here to here and from here to here. But if you look to the figure 2, the one they send it, or the one attached to it, they are saying that if this is 2r, either 2 uppercase r or 2 lowercase r, they mean the same thing. So this is a circle like this, and he called this is 2r, which is a diameter. And this is the center line. And this is the distributed load. The one I just found it, by the way, this one here, this is a Q sub O. He called it Q sub O. We call it sigma. The concept is a concept. So in this case, I know that, which is, this is sigma, which is P over A. And this is the dimension Z, which is the depth. Z in our case, he said that it is 24 feet below the bottom of the footing. So this Z is in our case 24 feet. But this is the center line. And this is the dimension X. If the load exactly under the center of the footing, X is equal 0. But as we move away from the center line of the footing, we need to know what is the distance X. Because this nomograph, how it works, we have an X-axis and Y-axis, and we have some dimension in the middle. So the X-axis is the influence value I. This here, or this here, or this here. All these are I's. Which is going to be used to plug it into this equation. That the sigma V is equal I times Q sub O, or times sigma, as I define it here. So this is the X-axis. These are the values. As far as the Y-axis, which is this vertical, it is the value of Z over R. Depth to the radius. The depth is Z, and the radius is given to be, this is 2R. That 12 feet, by the way, that's given. This is 2R. Either lowercase or uppercase. Some books, they are using uppercase. So I know the R, or the R is equal to 6 feet. Because 2R is 12. And Z is equal to 24 feet. So in order to get Z over R, so I will say that from here, I can say that Z over R is equal to 24 feet divided by 6 is equal 4. So this ratio is 4. And this is what you will see here. This is the vertical Z over R. Now we are coming to the distance X, which is series of curves as shown here. I'll use the green. It is the X over R. R is not the radius, it's not the radial distance, it's the radius. So these here, they are X over R. So these curves here, let me just highlight one of them. Not necessarily that one, the one we're going to use, but basically all these are the X over R. So I need to get X and R already known to me. And this is the most difficult part of it. If you look to the plan view of the problem, we need to determine which one is x, such that I can divide the or get the ratio of x over r. Where is the distance x? Where is the distance x? The distance x, according to this diagram, is the distance measured from the center line to the point, whatever the point is. If the point is here, so this how far is x. If the point under the load, exactly under the center of the load, the x is equal 0. As we go far away, the x is increasing and the stress increase will be lower, by the way, or smaller. So my x in this case is the distance from here to here. This is the x distance from the center of the load to the point of interest. I need you to remember that. Is not the this is 25 feet, by the way, and this is 25 feet also. And a common mistake that I can take 25 and consider this is a distance x. So in this case, the x is equal what? X is equal the square root of 25 square, Pythagorean theorem, and this 25 square. So this distance is, let me do it. So 25 square, and you multiply it by 2 and take square root, I get 35.36 feet. Now I can get the ratio that I need in order to get the influence value I. I need to get x over r. X in my case is 35.36 feet divided by r. We said that the r is 6 feet. So in this case, we have a number, the x over r, to be what? To be 35. So 6 divided, about 5.89. 5.89. So I have this number, and I have another number here, which is z over r. Now the business will start. And let me just increase the camera here like this. So I have two numbers. I have the z over r, which is the y-axis. I have 4. So here it is. Where is my 4? Here it is. My 4 is here. This is the 4. And I need to pick the x over r. The x over r, 5.89. So you can say about here is 5 and here is 6. So this is the 4, the 5.89, 5.89. This is 5 and this is 6. So 5.89, it is somewhere here. Something like that. Here it is. Use your best engineering judgment as far as linear interpolation. I know this is curved, but I think the answers that's given, or the answers that are given, it should be, if you look to the 4 possible answers here, they have 0.01, 0.02 double, 0.04 double the previous, and 0.1. So the difference is huge. So the rounding or reading the number from the graph is going to be a little bit Okay, so I hope that we are going to get one of these answers. Let us read together. So I have the z over r of 4. This is an easy one. And always I encourage everybody to carry a couple straight edges or couple triangles with you during the exam. You need to draw a parallel line or perpendicular line or something like that. So it's a good idea to carry 2 sets of squares with you, just in case. So I will move horizontally at 4 until I locate the point that I believe is close enough, 5.89, which is this number here. Okay. And in this case, I will go up and down. Here is the I, as I told you, it is the x-axis. So this is the I, and this is I, and this I, and this is also the I also. I should mention this also. This is I also, the x-axis or the horizontal. So in this case, I will move vertically. Something like that. Very close to 0.005. So if you get close here, and let me zoom in. So it is 0.005, a little bit beyond the 0.005. This is 0.0006. If you'd like to call it 0.0052, I have no problem with that. So in this case, I will say that the I is equal 0.005. If you'd like to put 2, I have no problem with that. So we are going to get the sigma v is equal to the influence value 0.0052 times q sub o, or sigma, the one we calculate. Do you remember sigma is equal b over a, or q sub o? It is 1.77 ksf. This is the dimensionless quantity, by the way. So if you finish this, you will find that we do have an answer to match this. 1.77 times is giving you about 0.0092 ksf, kbs per square foot. And you will find that, oh, he said most nearly, so probably I can round this to be about 0.01 ksf, and you will pick it and go home happy. And it turn out this answer is the wrong answer. So they are giving you 4 possible answers to accommodate or to match the common mistakes that we did. Remember, we have what? We have 1, 2, 3, 4. So this footing, it will increase the stress at point B by this value. But I do have 4 of them, my friend. So I have to multiply this by 4. Multiply by 4 and multiply by 4. If I forget the 4, you will find an answer. So in this case, the 4 times 0.01 is 0.04 ksf. And this is the delta sigma V. I will call it delta sigma V. This is the increase in stress. And in this case, instead of the answer A, it became the answer C. And this is the correct answer. So when you receive it, look at it and let me know. Okay. So these kinds of problems you might see either in the AM or the PM, I don't know, but it is a very important concept and we need to be aware of that because the stress increase. So I will make a copy of this and send it to you, and you will be you are very welcome to go over this when you receive it. And if you have any question, you can. There is another problem, I believe, in my book. Let me see if I have it. The one that the one I was looking for it in one of the exams. Probably is not handy, but I will locate it and see what. If you do have a rectangular load, I believe this is the one I used here in one of the problems. Rectangular, or yeah, it is very important to know exactly where he is looking, like the problem we just solved together, where for example this problem could be repeated again, and I need the stress increase under this here, under this footing number 2, for example. If I call this footing number 1, 2, 3, 4, what is the stress increase at the center of footing number 2 due to all of them? So in this case, I'm going to treat each one separately. This one here, under the load, under the center of the load, it will be different. This load here, from here to here, is a distance. From here to here is a distance. And from here to all the way is a distance. But here, since this point B is a common point between all of them, so the distance X to column number 1, to column number 2, to column number 3, or footing number 3, equal distance all the way. So I was able to calculate it once and multiply it by 4. I calculate the effect of 1 and multiply it by 4. And this is why I said that don't forget to multiply the 4, because if you did not multiply by the 4 here, that means that you are taking the influence or the effect of only one footing, which is not the case. He's asking for all of them. But if this question is changed such that he needs the stress increase under a different point other than this point here, so the calculation will be completely different. Okay, and I will be glad to include a problem like this in the future. I think I have something similar to this. And the rectangular ones is a little bit, we have to be careful also, because the dimensions, for example, this one here, this is what I was looking for. This is another nomograph that for a rectangular or a square. And let me grab a clean copy, and I will send it to you also. Yeah, and here it is. So I made a copy of these two sheets that I will also include it. And the best way to understand these things is to go to and the practice. And I believe I have some problems. I don't know if they are included in the, but this is again from the uh, Foundations and Earth Structures by the Naval Facility. At the bottom here, the source is given. So this is the vertical stress increase under rectangular load. And I said rectangular or square load. Square load. Sorry, square load. And they give us this here, the X and Y. And also we are looking for an I, influence value. But the influence value in this case is not horizontally, it is vertically. So the I is here, which is the same I is here. And there are two parameters I need to determine before I can pick the I, the influence. I need the value of M and the value of N. This is N as in Nancy, and the horizontal, the value of N, or the value of N at the bottom here. This is the N. And the series of curves, you can see this is the M. M as Mansour. What are the parameters that will contribute in determining M and N? They are giving here. M is X over Z, and N is Y over Z. And they mentioned that the M and the N are interchangeable. You can call this M, it does not make any difference. However, this diagram is very, very important, because the problems that you might see on the exam, they are not easy and straightforward. They are tricky in a sense that this is a dimension Y and this is dimension X. This chart will give you the stress increase at this corner here, at a depth Z, which is sigma Z, at this corner here. So the stress increase at the corner. And this is why if you are given a rectangular load or a square load, and he asks you what is the stress increase at the center. Do you remember the 4 footings? Here, the load is acting over this slab, for example, but I need the stress increase in the center. So in this case, I don't have a chart directly like this, but I can create a chart, or I can divide this load or break the area into something like that. So I will call this is area 1, area 2, area 3, area 4. So each area, whatever the dimensions X and Y, will be at the corner. So at the corner of each one, so I created something like that. And there are many, many problems related, by the way, to this concept here, because he's asking to get the stress at the center at a certain depth Z. But there is no such map give directly like this. I need to get So in this case, I can divide, I can play around, or I can divide unless the footing is a square. A square, which also it has a picture. Here it is, a square. They came up with this chart. Also, it is the same Professor Bosanik's stress contour chart. This for a square footing, and this for a continuous footing. Strip footing, they call it infinitely long footing. And they came up with the width B as in boy, and the pressure distribution is P as in Peter, and they came up with vertical distance and horizontal distance. The vertical distance in terms of B as in boy, this is the depth, and how far from the center of the footing, B or 2Bs or 3Bs and so on. So this is another way or another illustrations available in geotechnical books, and I made it here for you. I made a copy here so we can solve problems in the future related to this. Okay, so I will send all this to you in order to help you with this concept, because you might see a problem related to this, and I hope this will help you to understand that. This is something that I received an email from one of you, I believe, one or two, if I'm not mistaken. So I said, let me start with this so we can ensure that this subject is really clear. And when you receive it, I'm sure that you might come back with some questions. I have no problem with that. Uh, and uh, and as I said, that I will try to add this additional session that I owe you guys. Okay, and I will let you know. You will receive an email directly from the company that there is an update, and we will work it together. Okay. So the second topic, let me put this far away from here so at least I can include it, is the, according to this, I need to go over the soil classification. I started last time, and I told you there's a problem, I believe, in one of the practice exams that you received from me. If I'm not mistaken, let me try to remember which exam. It does have, yeah, either this or this. Yeah, here it is. This is the fall 2019 exam. This was sent to all of you last time. And I don't know how many problems did you solve so far, but please do your best, and I will do my best to get the solution, handwritten solution, or type solutions, it depends. So the problem that I referred to it last time is this problem here. Problem, this is a fall 2019 exam, and the grain distribution for a soil sample is given, and the liquid limit is given to be 34%, and the plastic limit, the PL, is given to be 19%. So the grain size distribution, it could be given to you in a form of a graph like this or a table. Both of them are subject to be included in the exam. And I will show you both. So this is a graph. This is the grain diameter in millimeter, and it is increased as we go this way. And this is the percentage the percent passing, and as we discussed last time, the two systems, the USCS, Unified Soil Classification System, or the Ashton system, both of them, they are depending on two parameters or two quantities must be known. I need to know the grain distribution, the grain size distribution, grain size distribution, either from the SIF analysis if the soils are coarse, or from the hydrometer if the soil is classified to be fine like silt and clay. So the grain size distribution must be given to me. The SIF analysis as you do for coarse like sand and gravel, and the hydrometer we use it for silt and clay. So this is the first parameter I need, or the first set of information I need, which is given to me in the form of a graph. It could be given in the form of a table. And after the first set of information, I need another, which the liquid limit and the plastic limit. Liquid limit and the plastic limit, where I can get the PI, plasticity index, PI, which is a liquid limit minus plastic limit, as you know. So the liquid limit is, in this case, 34 minus 19, which is a plastic limit. So this is going to give you 15%. We call these liquid limit and the plastic limit Atterberg limits. Atterberg's limits. Atterberg, he is a Swedish professor. Swedish, yeah, I believe it's Swedish professor. So the Atterberg limits are required. So liquid limit, plastic limit, and we can get the plasticity index and the other parameters. And this is why I believe, if I remember correctly, I asked you this question last time, and we'll solve it together. And this is from the NCEES, the AM, the Blue Book, where there was a question here, and we answered it together, if I remember correctly. Yeah, here it is. For those of you who attended the first time, forgive me for those who attended before. Sometimes I repeat things. So question 130 of the Blue Book, the most essential criteria for a proper soil classification using the Unified Soil Classification or the Ashton Soil Classification System are the water content, which, as I told you, we use lowercase w, and soil density, which is gamma. Atterberg limits, here we go, liquid limit, plastic limit, and the specific gravity, GS or SG, or a grain size distribution and water content, and finally a grain size distribution at Atterberg limits, and this is the answer D. So in order to classify the soil using the Unified Soil Classification System, or use the Ashton one, which is the A system, the Ashton system, both of them, they need the grain size distribution either in a form of a graph / table, or table or graph, and the Atterberg limits, the liquid limit and plastic limit, or it could be formed in a graph also given to you. But normally they give us numerical values and we enter because we are going to use something is called the plasticity chart. A plasticity chart. What is a plasticity chart? Is a chart, plasticity chart. They developed for us a plasticity chart to be used to identify or classify the fine-grained soil. As you can see here, this is a log scale. And if you go to the USCS in any book, you will find there is a chart and there is a table for the USCS. And this in chapter 7 of my book. Let me go very quick to chapter 7 to locate this chart. And yeah, here it is. The famous table and the chart. The USCS, Unified Soil Classification System. So this is the USCS. And this table is divided into three main categories or three main sections. This section here this is for the coarse-grained soil. Coarse-grained soils, which is the group symbol you'll find starts with G or S. G for gravel and the S for sand. So I have to decide if I am in this box or there is another box below it is for the fine. Here it is, the blue box. This for the fine grained soil, where you'll find that we have our ultimate goal is to pick one of these names or this group symbols. Okay, this is a single. We have double. We are going to do not double, dual. We call it dual segment, dual symbols. Sorry, I'm using double, no, dual, much better word. So for this, the gravel and the sand, here we are talking about the C for clay and M for silt and O for organic. Because since they are using the S1 time for sand, so they don't like to use the S again for silt. So they came up with M. Okay. And there is another row at the bottom. This one here, which normally some books even they drop it or they don't include it. This is for the highly organic soils, which is primarily organic matter. These type of soils, they are not suitable at all for any kind of foundation, because we need to know the type of the soil or the group symbol in order to determine the suitability of the soil for any kind of foundation that will be built or for any pavement job to support the pavement. So we need to know the group of the existing soil, and based on that we can determine how strong the soil is and if the soil can support the load or not, how much settlement will happen, and so on. And this is the purpose of the classification. There are some good soils and bad soils, and I'm sure that you already covered this in soil mechanics and in other classes like geology classes and so on. Normally this group, the one highly organic, which is, it has a simple PT. It is not normally, is not really asked because very easy, but we need to decide if we are in the this here or this here. In order to determine that I am in the upper box or the lower box or in the coarse or the fine, I need to know how much is the percentage retained on number 200. So the number 200 is very, very important, Sif. Number 200. And number 200 means that we have 200 openings per linear inch, not per square inch. So imagine there is 1 inch length and you have 200 openings. So how much the diameter of each one of them? This graph here, it doesn't show that. It doesn't show that. Some graphs, they have the diameter in millimeter and they put on the other side the size of the SIF. For example, let me see if my book is handy. Okay. But you have to be ready for both. You have to be ready for this or this. So, for example, you might see something like this. This is another grain size distribution. Bro, you saw this graph before. Let me see if, okay, something like that. Where, let me get closer. I know the, and zoom in. And I will tell you how to solve this issue. Okay, so here on the x-axis here, they give us the diameter in millimeter, particle diameter in millimeter, exactly as given. And this is a curve. But here, he gave us, in addition to diameter in millimeter, he's giving us the SIF number. For example, this number 4. And number 4 is very important, and number 200 are very important. These are the two numbers that I highly recommend you to remember the size, the opening. Because number 200 will separate the coarse or the gravel, the coarse aggregate, as we call it. So number four, it has 4 openings per linear inch. Anything retained on number 4, we call it a gravel. Or we call it coarse aggregate in concrete mixed design. So 4 means that it has 4 openings per linear inch. 1, 2, 3, 4. So the opening for number 4, 1 inch, as you know, is 25. 1 inch is equal 25.4 millimeter. I know you hate the SI units, but we have to deal with it. So if you take 4 openings, you divide this number by 4, will give you how many millimeters? But we consider the wire diameter. And this is why the diameter of the wire for number 4 should be subtracted. And this is why if you go to any ASTM book, you'll find number 4 is not 6 millimeter, as it is only 4.76. So number 4, the opening is not a quarter inch. As you can see, 1 inch divided by 4 is a quarter, but we subtract the wire diameter. So this is why 4.76 is number 4. So it is 4.76 millimeter. Or if you like to make it in inch, it is 0.187. It's not a quarter inch, it's not 0.25 inches. Because the wire diameter should be subtracted. So anything retained on number 4 is coarse aggregate. Anything go through, it could be sand or silt or clay, but the number 200 So number 200, which has 200 openings per linear inch. Again, if you don't, this is 0.075 millimeter or in inches. So we'll go 0.075 millimeter as the opening. Anything retained on number 200 is sand. Anything goes number 4 and is retained. Any number, anything that goes through it is silt plus clay. Silt is coarser than the clay. Clay is the finest one. So the size 4.76 and 0.075 millimeter is required for a problem like this, because unfortunately he did not give us the let me get the problem one more time. Here it is. Here he did not give me where is number 4 and where is number 200. So in this case you have to be ready. You have to say, okay, this is 0.1, and we said that number 4 is 0.4, so 4.76 millimeter. So number 4, I'll write it down here. Number 4 is 4.76 mm, and number 200, the 0.075 mm. And every time I solve a problem, or you solve a problem, I recommend you to remember this. Because I need to get the percentage, because I need to decide I am in the green zone, blue zone, sorry, or I am in the course. Okay, but the 4 answers here have S, S, M, and C. Oh, he makes all of them. I have sand, and I have M for silt, and C for clay. So how to read this? As I told you, it started from here, 0.01, and this is 0.1. So, and this is 1, and this is 2, 3, 4, and so on. So 4.76 millimeter, this is 4, and this is 5. So 4.76 is somewhere here. And 0.075, this is 0.01, 0.02, 0.075, somewhere here. And I hope that the graph that will be given to you, it is drawn to a good scale. So in this case, I can draw a parallel line here and get the percentage. Okay, so I will draw, try to do your best to be accurate as much as you can. And the other one is somewhere here, because number 4 is going to determine if I am So obviously the number 200, which is a 0.075, this number 200, if you would like to draw something like this, and this is a 200, and this is 12.5%, and this is 0, and this 25%, and so on. So if we go to this chart right now, or this table, say that I am on the top on the course size if more than 50% retained on number 200. But the fine, it is 50% or more passes number 200. So I have here only 12, and I have here, I have less than 12. I have almost 12, 11.5, or maybe 10.9. So what conclusion can we make from here? That if I have this, and we need to translate this into some kind of, okay, normally I said here it is number 200. What is retained and what is passed? Okay, normally, okay, so because they use these words a lot, retained and pass. Pass or passing, percent passing or percent. So you have the problem. Let me just take a few minutes break and come back, and we'll continue our discussion about this problem. Here it in the front. Let me zoom out. At least you can work on it. Already you have it. I think I sent it to you last week. So I don't know which answer did you pick. We will talk about this after I come back. Let me give me a few minutes and I will be back. Okay. Thank you. So right now it's about 10:15. Sorry, not 10:15, 6:15. 6:12, 6:12. So another 10 minutes or so. Thank you very much. Hey, welcome back everybody after this short break. So it is very important to know the sizes, the number 4 and number 200, since they are most frequently used. So based on this, this is 12 and a half, so probably this is 11 or 10 and a half. So that means that the percentage based number 200 is about 10 and a half to 11, whatever you like to call it. That means that the percentage retained is the difference between 100 and this, which is probably 89%. If we consider this 11%, and this number here, or 10 and a half, or 10, whatever you like to call it, make it 10, and make this is 90. So 90% retained. So immediately, the moment that I decide that more than 50% to number 200, I am in this box. So I am either S, which is sand, or G. So right now, by the process of elimination, I can eliminate two answers: the clay and the silt. So SW or SP? W stands for well graded and P for poorly graded. So the process of elimination is good, and we need to get benefit of the process of elimination by getting rid of the answers that does not make any sense or doesn't match our findings. So right now I am between these two, at least 50-50. If you have only 1 minute left, and by doing just number 200, and you know where it is 200 days, and you can narrow your choices 50-50 instead of 25%. This is 50-50, pick one. I have only 1 minute left, and I will pick one and pray to God. Maybe God will accept my prayer, and I will pass. But if you, right now, we are here. If you look to number 4, number 4 is another safe, which is very important. Here, I know the two answers left for me is S, well graded, and SP, poorly graded, which is the two answers here. SW and SP, which is the well graded sand and poorly graded sand. So the gravel is not part of my discussion. So I am not worried too much about number 4. Okay. But maybe they are going to mix the G and the S. So in this case, you have to. So we start from left after I decide which box and after that, I start to narrow my choices as I move on. If I am in the upper portion here of this section, I am in the gravel section. This was starting with G. If I am here with sands, I start with S. And if I am in sand, I have to go and narrow my choices and keep narrowing until you come to one of these answers, and this will be the correct answer. So if it's sand, if it is 50% or more, pass number 4, because I said number 4 is the one differentiate between gravel and sand. So I am in the sand, so I am here. So he said sands with less than 5% fines. What do you mean by fines? The fines, these are the one passes number 200. We call them fines, which is the silt and the clay. So I have here with less than 5%. No, I do have a sand, the other one. Sands with fines more than 12%. I have 10 and a half or I have 11. If I take 10 and a half or 10, I have 10%. So less than 5 and more than 12. I got confused. So I will move forward to see who is going to help me. We have two quantities. It's called C sub U and C sub C. And these two are given here as C sub U, uniformity coefficient, C sub U, and C sub C. And we need to get these two quantities. So C sub C is defined as D30% square divided by D10 times D60. And you don't have to memorize these equations. And the C sub U, uniformity coefficient, is equal D60 divided by D10. And in any geotechnical book you have, or any review book you are using, you will find the definitions of these things, and I cover this in the class. And C sub U, uniformity coefficient, uniformity coefficient, and the C sub C is called coefficient of curvature, C for curvature, coefficient. What does it mean D60 and D30 and D10? The gradation curve, if you look to the gradation curve, so if this is the gradation curve, and if this is the curve is given like this, can carry it all the way to the end, and this is the diameter, and normally this is log scale, diameter D in millimeter normally, and this is the percent finer by weight, the y-axis, percent finer by weight. So if this is 100%, so the D60 and D30 and D10 is like this. I will come at 60% and I draw a horizontal line to intercept with the curve, whatever curve this is. We'll call this D60. And the same story, D10, I come at 10% and draw a horizontal line until I hit the curve and come down. And we call this D10. This is how we determine the diameter, okay, for the 60% or for the 10% or for the 30%. So if we look to this, and if we can determine these quantities, so 30, for example, this is 25. So 30 somewhere here. And this is 62 and a half, 60 somewhere here. And 10 or 11 is somewhere here, the one we just found it. So basically, I will draw these horizontal lines and they try to get what is the D60 and D30 and I will come down and read them as accurate as I can. So this is the D30 and this is the D60, the diameter for 60% and so on. Please do it, and when we meet next time you can tell me if I got C sub C a number in the neighborhood of about 0.99, about 0.99, and C sub U I got a number of about 7.7, and again about, okay. So you got, so this will help these two numbers, the C sub C, the curvature coefficient, and C sub U uniformity coefficient, will help me to narrow my choices right now. So he said that when you have C sub U, and I will focus only the two answers at the left, which is SP and SW. So right now, for SP and SW, so I am here, SB or SW, well graded sand or poorly graded sand. So if you look to this, you will find that this here, C sub U is greater than, and C sub C between 1 and 3. And the second one, which is SP, it is C sub U less than 6 and or C sub C less than 1 or C sub C greater than 3. And again, there are footnotes here. Okay, we have a lot of footnotes, by the way. Okay, for example, the D, this define what is C sub U and C sub C. And a lot of footnotes, we need to pay attention to that. So I pick which one is the best. Okay, and they are looking what is the best answer. So I have C sub U greater than or equal 6. I have C sub U is about 7.7. And the C sub C 0.99 is very close to 1. Okay, is very close to 1. So the best answer right now, I am here, and they say the word and is very important, and because they are using or and. You have to pay attention to that. So probably the best answer right now is SW, because this will match the, and I selected the answer A in this case, which is SW, or the answer A. Look at it, and if you disagree with me, please let me know, and we can discuss it next time. The second approach is called the Ashton approach. And the Ashton approach is called the A system. The A system. Here, by the way, do I need to use the plasticity chart? Before I forget, this is the plasticity chart. It's given on the same. Mine, I have it a little bit bigger in my books. Try to draw it a little bit bigger as I can, or as here it is. For example, I have two of them in my, one is simplified and one detailed one. The one that has the A line and the U line and all these things, or the one has a simplified one. We can talk about this later on when we have a problem. Do I need to use the plasticity chart? No, because I don't have fines. Okay, I don't have the choice, which is sand with fines more than 12%. I have only 11%. So in this case, I need to classify the fines either ML or MH to get the SM, or I need to look to the other option, which is this one here, which I am not. So I'm talking about the C sub C and C sub U. So there is no need to use a plasticity chart because it's not required. For the second method, which is the A system, the Ashton classification system, this started way back in 1929 for the sake of determining the most suitable soil for pavement, because Ashton is started with the pavement. So they came up with this a chart, and again, this chart is, can say, divided to two main sections. This one here, and this is where granular materials less than 35% passing number 200. And the other section of this table is the blue one here, which is the section where more than 35% passing number 200. This is the silt and the clay material. This is gray, if you like to call this is coarse, and this is fine. I have no problem with that. And they start with A1 and A2 and A3 and A4 and A5 and A6 and A7. The A7 is divided, by the way, A7-5 and A7-6. There is another column here, by the way, but it's dropped. Some books, they have it, which they call it A8. A-8. This is the worst soil. It is very bad soil. It has a lot of organic materials and is not suitable at all for any kind of roadway design. So some books they have it, some books they don't. For example, here, but generally speaking, we're starting from A1. Yeah, here I have it here, but I said that based on the Ashton soil classification system, soil A1 is being considered the best soil as a pavement subgrade. And while soil A8 is highly organic, not suitable for pavement subgrade. So this is why the A8, some books they have it, some books, this table for some reason that we adopted this table is not, I believe, adopted from Ashton, so from the NCAA, sorry, so they didn't show the A8, but the A8 is the worst one. Like the previous table, as I told you, for the Unified Soil Classification System, we have this row here, which is PT. This is a soil that even some books, they drop it completely because it is just classified very easily. If any soil has all these bad things here, so it's classified as BT and so on. So the same story with the Ashton. So the Ashton, we need to determine the percent basic number 200. So if you remember number 200, we have what? We have only 10% pass. So number 200, based on this, here is number 200. So I have about 10% or 11%, and what is left here is 90%. This called retained, and this called passed. And if the information given you in a table form, by the way, be careful because the retained versus pass is very, very important. So the percent finer, this is called fine material. This is fines. Anything passed through number 200, we call them fines. So it is just 10 to 11%. So it is less than 35%. So less than 35%. So I am here. So I am in this box because I have less than or equal to the number 200. I have only 10% or 11%, whatever number you agree with or you agree with me. So I am here. Since I am in this box, I will limit my discussion. So I said that number 10, number 40, and number 200. And by the way, the sizes are here. Do you remember the 0.075 for number 200? If you forgot, it is mentioned here. And after that, they are saying that what is the liquid limit and the plasticity index. Liquid limit is LL and PI. Plasticity index, which is the difference between liquid limit minus plastic limit. In our case is the PI is a liquid limit minus plastic limit. So the liquid limit was given to be 34 as indicated, 19. So this is 15%, which is a PI. Plasticity index, not the point of intersection as we use it for horizontal curves. So I am here right now. So number 200, I have less than 15% or equal, less than, almost, this is 10%, less than 35, less than 35. So any of them could be really, except this one here, the 10%, yeah, A3 is out. But if you look to the liquid limit is the 34% that's given. So I will come here for the liquid limit and see less than or equal 40, yes. A greater, no, this is out. Less than, yes. A greater than, this is out. So the process of elimination eliminated 2. Let me get closer here, you can see it. And I will go to the plasticity index, PI. So I am either this or this. This is the plasticity index is 15, the one I got in my. So I am looking to these two options. For the plasticity index PI, you will find that less than or equal 10, so this is out. Greater than or equal 11, so it is A26. And this is why I will select the A26 as my choice. Add the soil classification based on the Ashton classification system. There is another thing that it may be added. It can give you A-A26, and they put a number here, A2-6, and put a number here. Okay? And we'll see if this is applicable to this case or not. There is something called GI. And if the soil classified A4 to A7, I need you to be aware of that, in the fine only. Okay? Let me, I don't like to use this example because, which is A7 or A6, A6 is good. A6, okay, not A26, let me just A-6 and put a number in parentheses here, and at least to get. So if the soil is classified to be fine, they give us additional number. They may be associated. So A6 and A-6 if the soil is, and they put what is known as the GI. So if the soil is classified between A4 to A7, and by the way, the A7 is divided A7-5 and A7-6 based on these two equations. And I have some problems, by the way, that we need to test to see if it is the soil is A7-5 or A7-6 based on these two equations here. But let's focus on the GI. Then calculate the group index. Okay. The higher the GI, the less suitable soil. I needed to know that. And this is the equation for the GI. So the GI is applicable to the fine grained soil only, which is the silt and the clay. So you will find that the GI is equal F minus 35 multiplied by this liquid limit, plasticity index, all these things. So, and if, by the way, just for the sake of, to make sure that If the computed GI is less than 0, because we have a negative, by the way, we use GI to be 0. GI cannot be negative. So the GI cannot be negative. So the GI, if the calculation indicated or ended with a negative quantity, less than 0, we use the GI of equal 0. And I need you to know that the higher the GI, the less suitable the soil. For example, A6 with GI 15 is less suitable with A6 with GI of 10. Okay? So the higher the number for the GI, the less suitable as subgrade material. So the soil with the lower GI, the better. Okay? So this is one thing that you remember. This is one of the cases, the lower number, the better. Okay? The lower number, the better. Okay? Like the blood pressure. Okay? Let me remember the blood pressure. When your blood pressure is normal or low, is not high, so that's good. Okay? So the same story with the GI. The GI, okay, the higher the GI, the better, like the high blood pressure. Okay, let me put it that way. Okay, if you'd like to remember it as, okay. And there are some charts available in some textbooks like this for um, soil classification based on, to make it easy. But if you follow this, you will be in very good shape. Okay, so this is as far as the soil classification, and I hope that you. So the answer is B as in boy. And when I scan it and send it to you, probably you didn't get my problems last week, so it will be very good. The problem, while I was looking for this problem, I came up with this problem. I came across this problem here, which is a problem 15 of the fall 2019. This is a concrete mix design problem. I talked about this before. We need to pay attention to the adjustment. So I don't know how many of you solve it, and sometimes I do this. I add the none of the above, not to confuse you or to challenge you. No, I need you to, I know the actual exam doesn't have the none of the above, but let me give you a clue here, and you are very welcome to look at it. If you solve it, that's good news. If you didn't solve it, it's still good news. At least you have a chance to solve it. But when we are talking about concrete mix design or earthwork, there is something common in between, which I indicated last time. So the concrete mix design or the earthwork calculations, there is some kind of similar or analogy between these two as follows. For the concrete mix design, we look to the SSD, not the stopping side distance. This is a saturated and surface dry as my ideal condition. The aggregate could be below the SSD, which is dry. And the aggregate also could be, or the aggregates, because fine and coarse, they could be higher than the SSD, which is wet. If from the dry condition, either air or oven dry, to the SSD, we need to add more water, which is called SSD moisture content or moisture percent. but between the dry and the wet is the moisture content only, which is W, or water content, moisture / water content. And this is how we make the adjustment, by the way. And we need to understand this very well, because the most confusing part of the concrete mix design is the adjustment for surface water. So if we do, this is the SSD condition, which is saturated. This is the ideal condition, or this is the basis for design. This is the ideal condition, ideal. If the aggregates above the SSD, they are in the wet. If the aggregates are on the dry side, here we have extra water, here we have deficit. For the earthwork, we have something similar to this, which is the loose cubic yard, and this is a bank cubic yard or a cubic meter, and this is a compacted cubic yard, CCY. I always draw these two diagrams like this, and they are available in my books. I prefer diagrams, tables, and the charts because you could remember these things easily. So if from the bank cubic yard to loose cubic yard, we have a factor, which we call it a swell factor. And the swell factor is greater than 1. And the swell factor is equal 1 plus a swell percent. And the swell percent must be given to you. Don't assume it. Between the compacted cubic yard, by the way, the compacted cubic yard is the finished product, finished product. This bank cubic yard, this is the soil in its natural state before excavation. So natural state, natural, as God created or as exists. Loose cubic yard, this is after excavation. So from here to here, we have something is called a shrinkage factor. Which is equal to 1 minus shrinkage percent. Okay, this shrinkage factor is less than 1 for all the soils except rocks. For sand, silt, clay, name it, all these or mixtures, is a greater than 1 for rocks. Because when we blast rocks or we disturb rocks, you cannot put it back again as originally exist, as God created, so it will increase in the volume, it will never shrink. But the sand, clay, silt, or any mixture, you will find that. So if we are able to remember these relationships in a drawing like this, I believe you will be able to solve these two types of problems so easily. And I hope these diagrams can help you. For example, the problem I'm talking about here in practice exam fall 2019, he gave you that concrete mix has been prepared based on this ratio. There are two methods for mixing concrete, either the absolute volume method or the ratio method. The ratio, this is the old method that my grandfather and your grandfather used to mix concrete. So the ratio means 1, for example, in this case, to 1.9. to 2.7. What does it mean? It means 1 part cement, 1.9 part for sand, and 2.7 for gravel. This the standard notation for mixing concrete by ratio. 1 part cement, 1.9 parts for sand, and 2.7 parts for gravel. This ratio normally by weight, not by volume. If it's by volume, it can be solved, but normally the ratio is by weight. And he's asking to find what is the water cement ratio. He's asking for the water over cement. And this is the ratio by weight, by the way. This is water over cement. And this ratio by weight, how many pounds of water to how many pounds of cement. And believe me, after I explain this problem, if we're able to finish it tonight, or because I have to leave a little bit early, or next time, you will be able to mix concrete in your backyard and you will be fine. Or sometimes we express this ratio, by the way, how many gallons of water per 1 sack of cement. Because we know a gallon of water, as all of you know, it is 8.34 pounds. And a sack of cement, as all of you know, is 94 pounds. So the ratio is by weight. But during the exam, I know we are relaxed here and you have some kind of tea or coffee or something nice next to you and you are sitting and relaxing. During the exam, under the pressure of the time, obviously, you are struggling with time, so you are working extremely fast. And so the cement, specific gravity of cement is 3.15. And this is for all types. As you know, type of cement, we have type 1 and type 2 and type 3 and type 4 and type 5. And I talked about these types before. And they have some questions about which one is the most suitable type for certain application. You need to know the 5 types of cement based on the ASTM C150. So all types of cement, we are using one fixed number, specific gravity 3.15. The SSD sand, okay, the saturated surface dry moisture content for sand is 0.45%. What does it mean? It means that the sand, which is a fine aggregate, needs to absorb 0.45% of its own weight from the dry condition to reach SSD. This is what is meant. So if I have a piece of gravel like this, and this piece of gravel is dry, completely dry, this will absorb some water to fill all the internal holes or pores, and the surface is saturated inside and or the inside and outside saturated, and the surface is dry. It's called SSD, saturated and surface dry condition. So the soil or the gravel, sorry, in this case, is saturated, but it's dry from outside. So it will not give water, it will not absorb water. This is what is meant by SSD. SSD means saturated and surface dry. It is saturated, but the surface is dry, which is self-sufficient as far as water. It will not give, it will not take. It's saturated to a degree that It will not give or take. The second given piece of information for the coarse aggregate is 0.85. The added water, how many gallons per sack? He gave you 5.9 gallons per sack of cement. The air, it is always the air by volume, not by weight, because how much the air weighs, not too much. The aggregate used for the mixing, it does have a moisture content, 4%, and the wet coarse aggregate has a moisture content of 0%. That means it's dry. So the sand is wet. I don't know if this is a typo or I meant really is 0%. I need to double check this, but we can calculate it and see what. It could be I meant that 0%. So it is not, it's a dry. So there is no need to mention if it is really my intention to make it 0. So there is no need to add this here. Specific gravity for sand is given. Specific gravity for coarse aggregate is given 2.6. Specific gravity for cement. So we have a lot of information. And my ultimate goal is to get the water cement ratio. Remember, he added 5.9 gallons. So if you like to look to the water cement ratio based on this amount of water only, so the water over cement, water he said at 5.9 gallons times 8.34 pounds per gallon, divided by sack of cement 94 pound. If you calculate this ratio, sometimes they add this number to make it attractive for us to calculate it and go home happy, but this is the wrong number for sure. So if you take 5.9 gallons and 8.34 pounds and 94 divided, it's 0.52. Let me use the same color. And 0.52. And you will find 0.52 is the answer A. But this is not the intent at all. This is true only if both aggregates are at the SSD condition. But it's not. One, it does have extra moisture content, and one is completely dry, assuming that this number is correct. So we do have what is known as the adjustment for surface water. So if the aggregates, so if the coarse and the fine aggregates so if the coarse aggregate, which is a gravel, and if the fine aggregate also, which is the sand, if either one of them or both of them are not at the SSD, are not either one of them or both, not at, so adjustment for surface water is required. Adjustment for surface water is required. And we need to know how to do this adjustment for surface water. Okay, and this is what I will start with next time because I have to leave. I know I'm leaving a little bit early, 20 minutes or so, because I need to go and bake something for the family before So I will scan these things and send it to you. So keep working on the 3 practice exams I gave you, and I will do all my best to come up with the solutions, handwritten solutions. At least I can send it to you. At least you can look at it. And I will add one more session because, as I told you, I owe you one session. Where is this things here? Where is the? Yeah, here it is. So today is the so I will add one more session. 6 so 6:20 before or after, I don't know. I will look to my schedule because, but in the month of June, hopefully I can squeeze it in the month of June because July I will start. As you know, the exam is going to give you the 22nd and the 23rd. And I believe the webmaster, he put something on our website, if I'm not mistaken. He put something on our website. They start, by the way, they start the, let me see if I can get this thing smaller. Here we go. Here it is. This is what we put on our website that, where is it? Here it is. Per NCEES registrations, okay, for October 2020, B exam, paper and pencil, okay, exams, okay, will be open or already open June 1st. And the exam will be taking place on October 22nd and the 23rd. So they split, instead of Friday only, they added Thursday to accommodate because the exam was canceled. So go ahead and whatever your decision, whatever what time you are planning this October or next year, go to the NCEES the website. They have all the information. We don't involve in that. I always ask everybody to go to the NCEES and get all the information. Ask them for any information you need, and I will do my best to help you guys as much as I can. And I'm sorry that I have to leave right now. So you can email me, info@pastb.com, which is very easy email, and I will be doing all my best to help you all the way to this. Stay away from Corona, by the way, from this COVID-19 coronavirus. Please stay healthy and pray for me to stay healthy, and I will do all my best to help you. Thank you very much for coming tonight, and I appreciate your presence tonight, and I hope that you enjoyed it. And if you have any question, just email me, and I will do all my best to come back to you as soon as I can. Thank you very much. Good night, everybody. This lecture, by the way, it will be loaded here, free workshop videos. Somebody will convert it, and after that loaded on the system. It takes about 2 or 3 days, or maybe sometimes 4 days, because they are working from home and they are doing all their best, my staff, to help me during this crisis, because nobody is coming to the office. So I am the only one here today. Okay. Thank you very, very much, and I appreciate your help, and enjoy the rest of your weekend. I will be here tomorrow, okay, for the transportation and for the seismic. Thank you very much. Bye-bye.